This is lecture 1, segment 2. Hope you've all understood the topics of segment 1. In this segment, we'll be studying empty set, universal set, equal set, subset, and at last we'll see the Venn diagram representation of sets. And we must see different type of examples under all of these topics. So first comes empty set. What is an empty set? From the name, we can assume that a set having no elements in it is known as empty set. So when the total number of elements of a set is 0, then it can be called empty set. As we can remember, we use curly braces to express a set, right? And we write down all of the elements of that set separating by comma, right? This is how we express a set in tabular format. And as we know, empty set has no element in it, so there will be no element within these curly braces. So this is what we use to express an empty set. And sometimes we use phi as well to express an empty set. We use phi and curly braces. Okay. So if someone writes A equals to phi, then we understand that A is an empty set. So A will have 0 element in it, right? Yeah. So now we know what is an empty set. Here comes universal set. Before we go into the discussion of universal set, let's consider 3 different sets A, B and C, where A equals to 1, B has 2, 3, 4 as its elements, and there are 3, 5 in set C. So what is a universal set? A universal set is a set containing all of the elements of the sets under consideration. So here, since we denote a universal set by capital U, the universal set will contain all of these elements under the set of which are considered. So the elements will be 1, 2, 3, 4, 5, and let's check if there any elements missing in U. No. So universal set U will contain all of the elements of the sets under consideration. So you can ask, why haven't I written 3 twice here? Because 3 appeared twice in B and C. As we can remember from the definition of set, set is a collection of unordered different elements. So here, if we would write 3 twice, then there would be 2 same elements. So eventually that wouldn't change anything. So U equals to 1, 2, 3, 4, 5. Let's have another example. For example, X is the set of 2 colored, red and purple. Y is a set of instruments, musical instruments basically, guitar and piano. And Z is a set of 3 numbers, for example, root 2, root 3, root over 5. So can we determine U considering all of these sets? Let's see. Universal set U will have all of the elements, right? So there will be red, purple, all of the elements of X. There will be guitar, piano, all of the elements of Y, and there would be 2, root 2, root 3 and root 5, all of the elements of Z in U, right? So what is the definition of universal set? I repeat, a universal set is a set that contains all of the elements of the sets under consideration. Okay, now we'll discuss about equal set. So when do we call 2 sets to be equal? Okay, let's start with an example. For example, set A is equal to 10 100 and 1000, and set B has 1000, 10 and 100. So from this example, it can be easily observed that all of the number of elements of A and B are equal, and that is 3, right? Both of them have 3 elements in them. So can we see if there is any element in B that doesn't belong to A, or if there is any element in A that doesn't belong to B? No. Here 10,000, 10, 100 and 1000. Here 100, 10 and 1000, 10 and 100. So all of the elements of A and B are same. So we can claim here that A equals to B. That means set A equals to set B. So you can ask, does the order of the elements matter here? No. From the definition of set, we can remember that set is a collection of unordered different elements. So the order of the elements doesn't matter here. So what will be the definition of equal sets? When two sets will have equal number of elements and all of the elements of them will be same, then those two sets are equal, right? Okay, we can see another example here. A, B, Z. Here A, B, Z, X. So can we claim these sets to be equal? No. We all can see that X doesn't belong to P. So the number of elements of PQ or are not same. So P not equals to Q here. But if we erase X, now both of their number of elements and their elements are same. So we claim here that P equals to Q. As simple as that. Okay, now we understand when we call two sets to be equal. So now comes subset. Our topic is subset. So we'll start it using an example. For example, set R equals to 10, 25 and 30. Set S 10, 30. Okay? So it's easy to observe that all of the elements of set S belong to set R, right? Here 10 and 30 belong to S and 10 and 30 belong to R as well. So when all of the elements of a set belong to another set, then the first set is called to be the subset of the second one. So the S is a subset of R, since all of the elements of S belong to R, and we write it like this as well. Okay, this is the notation, or this is the notation for subset. S is a subset of R, and now we let's see here. There is another example. 1, 2, 3. B equals to 1, 2, 3. So last we studied equal set, and now here we see A and B have 3 elements and all of the elements are same. So we can easily claim that A equals to B, right? But one thing, all of the elements of B belong to set A. So can't we claim that B is a subset of A? Definitely. And all the elements of set A belong to B. We can claim that A is a subset of B. So we have learned a new thing here, that is, if we have to prove two sets to be equal, we can first prove the second set to be the subset of the first one, then the first set to be the subset of the second one, and then we can claim using both of these statements that A equals to B. Okay? Yes. So now we know what is a subset, but we are yet to know what is a real subset. What is a real subset? So from the previous example, R equals to 10, 25, 30 and S equal to 1030. S equals to 1030. Okay, so are these two sets equal? No, because there is an element in R that doesn't belong to set S, but S is already a subset of R. So what is a real subset? When a set is a subset of another and both of them are not equal, then the first set is called to be the real subset of the second one, right? I repeat, set S has two elements. All of those two elements belong to set R, but set R has such an element that doesn't belong to set S. So S is not only a subset of R, but also S is a real subset of R. This sign is known to be the notation for real subset. Okay, real subset. Okay, now we know S is a real subset of R. And can I ask you something here? If A equals to B, A is equal to B, can I claim that A is a real subset of B or B is a real subset of A? No, both of the statements are wrong. Why? Because from the definition of real subset, we knew that if A has to be the real subset of B, then A must not be equal to B. But at the very beginning, it was declared that A equals to B. So if two sets are equal, then none of them will be the real subset of another. Okay? Okay. So now we know what is real subset. We can ask another question too. Here, for example, set M equals to A, B, C, D, and set N equals to A, B, D. So, first question, if M is a subset of N? No, because M has more elements than N here. So, N is a subset of M. Why? Because all of the elements of N belong to M. If M is a real subset of M? Yes, because since N is a subset of M and since N not equals to M, so N is a real subset of M. Right? Okay. Okay. Now we know how to determine if a set is a real subset of another. We have our last topic here, Venn diagram representation. Before we go to study Venn diagram, we have to know that John Venn invented Venn diagram representation of sets. Basically, it is a graphical representation of set theory. So, how to do it? Here, we studied universal set. John Venn expressed U, that is universal set, using a rectangle. This rectangle refers to universal set. And if we consider set A and set B, those two sets are considered here. We express sets using circles according to Venn diagram rules. Okay, we express sets using circles, and sometimes if for example say A belongs to A, capital A, that means small a is an element of capital A. Sometimes a point is used to refer to an element of a set, right? So if we put some dots here and write P, Q, R, S using small letters obviously, so we claim that P, Q, R, S, P, Q, R, S belongs to set B, right? Okay, this is mainly the basic rules of expressing sets through Venn diagram. So let's see if A and B are two sets that we are considering now. Where should we put those two circles here in this diagram? Should those circles be outside this rectangle? No, since we all know that all of the sets under consideration are subsets of U. I repeat, all of the sets under consideration are the subsets of U. So this area or this region refers to all possible elements of the sets under consideration. So since A, B, C, all of them are subsets of U, so we must put all of these circles inside this rectangle, right? So this is A, this is B, and this is C. And here we claim that if we know that small a belongs to set B, small a belongs to set B, and this is an element of set B, then we put this dot here, and this is known to be small a. And this is how we represent sets using Venn diagram. Okay, let me ask you something. If it is declared that A is a subset of B, A is a subset of B, right? Then what will be the Venn diagram representation for these two sets? For example, this circle refers to set B. And as we know, A is a set that is a subset of B. So all of the elements of A belong to set B, right? So can we just put set A outside B? And what if we put A outside B? Let's see. This region refers to the elements, or this region contains all of the elements of set A. And as we know from the statement, all of the elements of A should be there in B, right? But if we put A outside, these elements stay outside the region of B. So A must not be outside of circle B. Okay, now if circle A intersects circle B, then you can say that this region, all of the elements of this region belong to both A and B. But what about this region? These elements stay outside of B. But since according to the statement A is a subset of B, no elements of A can stand outside circle B. So we understand that A cannot be outside circle B and A cannot intersect circle B. So the subset A must lie inside the circle B. Okay, this is how we express two subsets, right? Now, can I ask something? That if A equals to B, what about this? What will be the Venn diagram representation of the sets? Can it be like this or like this? No, we cannot express A and B in either of those ways. Why? Since A equals to B, that means all of the elements of A belong to B and all of the elements of B belong to A. So there must be no region of B outside set A be no region of A outside B. So both of the equal set A and B will be represented by same circle.